Welcome to another deep dive. And, today our mission is to unpack this really fascinating, honestly, kind of high stakes technical detective story. It is all about speed, math, and, well, the danger of plausible garbage.
Yeah, plausible garbage is probably the best way to describe it, because this is something that could literally cost an algorithmic trading firm, a catastrophic amount of real money if they blindly trusted what they were looking at.
Right, exactly. So imagine this. You take a massive trading algorithm, like a full parameter suite backtest, right? And you port it over to a shiny, brand new Apple M2 Max GPU. You hit run, and it is fast. Like it runs 2,796 times faster than it used to.
Which is an insane speed up. Anyone would be thrilled with that.
Oh, absolutely. And it doesn't crash. It throws absolutely zero warnings. The equity curve it spits out looks perfectly normal, showing you, exactly how much money the strategy would have made. But there is a massive catch.
A really big one.
The core moving average cowering that entire trading strategy is just wrong. And I don't mean off by a tiny fraction of percent. I mean, it is wrong by a factor of 211.
Which means the entire foundation of the strategy is mathematically corrupted. But the system is just, serving it up to you as a total success.
Yeah, so how does a machine that incredibly smart fail so politely? That's what we're getting into today. We are unpacking this incredible technical article titled The GPU Precision Trap, How an fp32 Backtest on Apple Metal Silently Returns Garbage.
It's a great read. Really eye-opening stuff.
It is. We're going to figure out exactly why Apple's hardware forces this very specific error to happen, how the math completely breaks down behind the scenes, and the surprising fix that doesn't actually require you to go buy a bigger, more expensive computer.
And I think the overarching lesson here is just crucial for anyone listening. If you don't understand the physical, hard-coded limits of the digital playground you're working in, you're eventually going to get hurt.
Yeah.
You can't just trust data simply because a really fast machine gave it to you.
It honestly feels like driving this high-end supercar, right? But with a completely broken speedometer. So the dashboard is happily telling you, hey, you're cruising at a safe 60 miles per hour, but you look out the window and you are actually going 12,000 miles per hour.
Yeah, and the car just thinks everything is totally fine.
Right. So to understand how the math fails so spectacularly here, we first have to look at the engine of that supercar, which is the Apple Metal GPU itself, and how it actually physically holds numbers in its memory.
Let's start with the standard baseline first. If you are running a backtest on just a normal computer processor, a standard CPU, using Python and everyday data tools like NumPy, you are almost always operating in what is called double precision.
Okay, double precision.
Right. In computer science, this is known as fp32.
Meaning the computer is dedicating 64 bits of physical memory space just to hold that one single number.
Exactly. That's the physical reality of it. And 64 bits gives you this massive exact integer limit.
And just to clarify, the limit is basically the point where the computer can no longer accurately count by ones, right?
Yeah, that's exactly it. In float64, you can count exactly integer by integer all the way up to about 9 quadrillion.
Wow.
Yeah, that is a 9 followed by 15 zeros. 9 times 10 to the 15th power.
So you basically have an infinite ceiling for standard everyday math. You are never going to accidentally hit 9 quadrillion just counting daily stock prices or normal trading volumes.
No, definitely not. At normal price scales, you have more than enough margin. You're totally safe. But the trap springs the exact moment you take that exact same Python code and you move it over to Apple Silicon to speed it up.
Ah, okay.
Yeah, whether you are using the metal shading language directly or, frameworks built on top of it like MLX or PyTorch MPS, you completely lose that massive headroom. Apple's GPU architecture simply does not offer fp64 precision at all.
Wait, really? There's no fallback mechanism. You can't just tell the system, hey, I'm okay if this runs a little slower today. Just please keep my 64 bits of accuracy.
Nope. The architecture just doesn't support it for these kinds of raw compute tasks. The literal second your computation touches that GPU, you are forced down into single precision. fp32.
Or fp32, right?
Right, fp32. You don't ask for it, it just happens automatically. And fp32 is a dramatically smaller box. It can really only hold about 7 significant decimal digits.
Okay, let's translate that smaller box into a hard number for the listeners. Where is the exact ceiling for fp32? Where does the math actually stop being reliable?
So that exact integer limit drops all the way down from 9 quadrillion to about 16.7 million.
Wow.
Yeah, roughly 1.6 times 10 to the 7th power.
That is just a staggering downgrade. You go from basically infinite down to just 16.7 million.
It really is. And the really
Yeah.
dangerous part is what happens when you cross that 16.7 million threshold. The precision doesn't just like slowly fade out or degrade. It falls right off a cliff.
What do you mean?
Beyond that number, fp32 literally lacks the physical memory bits to represent consecutive integers. So it just starts skipping numbers entirely.
It's like you're suddenly using a calculator that only has a 7-digit screen. And I mean, 16 million sounds like a fairly large number if you're, I don't know, counting apples in a bucket. But when you are crunching millions of rows of high-frequency financial data, you just blow past that instantly.
Exactly.
But, well, hold on. Let me just run those numbers in my head for a second. If I am backtesting a strategy on Bitcoin, you know, the price of Bitcoin right now is around 30,000. 30,000 only has 5 digits. It easily fits on that 7-digit calculator screen. It is way, way smaller than 16 million.
Right.
So if the actual input data is that small, why is this hardware limit even a problem? Where is the actual danger coming from?
So that logical leap right there, that is the exact trap that catches so many experienced developers.
Oh, really?
Yeah. You look at the inputs, like a price of 30,000, and they fit perfectly. Then you look at the expected outputs, like a moving average of around 30,000, and hey, they fit perfectly too.
Right, they're fine.
But the danger doesn't live in the inputs or the outputs. The danger is hiding in the intermediate steps. It's hiding down in the hidden mechanics of the algorithm itself.
The middle ground where the numbers secretly balloon up behind the scenes.
Exactly. Let's look at the specific strategy that was analyzed in the article. It relies on something called a weighted moving average. Specifically, they were using a whole moving average calculated over a window of 150,000 bars of historical data.
Let's pause and unpack that for a second for everyone. When we talk about a parameter sweep backtest, we aren't just calculating this 150,000 bar moving average once, right?
No, not at all.
We are telling the computer to test thousands of different variations, like maybe a 10-bar window, then an 11-bar window, a 12-bar window, across millions of data points to see which specific combination would have made the most profit.
Right. That is the core of algorithmic backtesting. And it requires an astronomical amount of raw computation. So to actually get this done in a reasonable time frame, performance-minded data scientists use this brilliant algorithmic shortcut to speed it up.
Okay, what's the trick?
A trick called a prefix-sum, and it operates in O of n time.
Just to make sure we're keeping the math grounded here, O of n just basically means the time it takes scales strictly linearly with the amount of data, right? Like if you double the data, it only takes twice as long, rather than completely spiraling out of control exponentially.
Exactly. It's highly efficient.
So how does this prefix-sum trick actually achieve that linear scaling?
Okay, imagine you want the sum of a 200-day window. The slow way is to add up all 200 days, record the answer, then move forward one day, and add up the new 200 days all over again, completely from scratch.
Which means you're recalculating the same days over and over.
Right, it's terribly slow. The prefix-sum trick changes the game entirely. You just keep a running global tally from the very beginning of the data set. When you move your moving average window forward, you just look at your running tally, you add the new day coming into the front of the window, and you just subtract the old day falling out the back.
Ah, okay, that is really clever. So
Yeah.
you completely avoid recalculating those 198 days in the middle over and over again. You're just doing basic addition and subtraction at the arrows.
It's incredibly efficient, and it aligns perfectly with how computers prefer to operate, crunching big arrays of numbers all at once. But here's the twist. For a weighted moving average, you don't just keep a running tally of the price itself. The actual mathematical formula requires the code to keep a running total of the bar's index number multiplied by the price.
Wait, the index number?
Yeah, so like bar 1 times the price, plus bar 2 times the price, plus bar 3 times the price, and so on.
Oh, I see. Meaning, by the time we get to the very end of our massive data set, the last single calculation is bar number 150,000 multiplied by a Bitcoin price of 30,000.
Right, which comes out to 4.5 billion, just for that one single step. And remember, the algorithm isn't just holding that number. It's keeping a global running sum of all 150,000 of those continuously growing terms.
Oh, wow. Yeah, I totally see where this is going now.
Yeah, by the time the code reaches the end of the data set, that hidden running sum reaches roughly 3 times 10 to the 14th power.
Wait, but Earlier, we established that the fp32 hardware ceiling, like the absolute physical limit before the GPU starts violently skipping numbers, is 1.6 times 10 to the 7.
And our hidden running total just hit 10 to the 14th.
That means we just overshot the hardware safety net by 7 entire orders of magnitude. The intermediate number inside this algorithm is literally 10 million times larger than the space the Apple GPU has available to hold it exactly.
It's massive.
So what actually happens inside the computer when you force it to hold a number that large in a 32-bit box? Does it just break?
Well, it introduces something called the ULP. That stands for unit in the last place. This is essentially the physical gap between two representable numbers at that specific scale. And at 10 to the 14th power in fp32, the ULP is about 8 million.
Wait, I want to make sure I understand this. So the GPU can't count by ones anymore, it can only count by increments of 8 million.
That is the physical reality of the hardware at that scale. Your running sum isn't exactly 3 times 10 to the 14th. It is 3 times 10 to the 14th, plus or minus a completely random noise floor of 8 million. You're permanently carrying around 8 million units of pure rounding error.
That is wild. Okay, so we've artificially manufactured this massive, incredibly noisy intermediate number just to make the calculation scale faster. But at the end of the day, to actually trade, we still have to get our moving average out of it. We have to extract a normal Bitcoin price of around 30,000 back out of this absolute monstrosity.
And this is where we hit the absolute mathematical disaster. To find the moving average for a specific window, the algorithm takes 2 of these massive running sums, and it subtracts one from the other.
Okay, let me try to visualize this math. We are taking a massive number, which has a plus or minus 8 million in invisible rounding noise, and we are subtracting another massive number, which also has a plus or minus 8 million in noise, all to find a true price difference that should be around 30,000.
Exactly. In numerical analysis, this phenomenon actually has a very specific, ominous name. It's called catastrophic cancellation.
Catastrophic cancellation. That literally sounds like something out of a sci-fi movie.
It really does. But the reality is just math failing. The signal you are looking for, that 30,000, is completely swallowed by the noise floor of 8 million. Once you do that subtraction, you lose all your significant digits. The true data is literally vaporized.
Unbelievable.
And the resulting moving average that gets spit out at the very end, the author of the article actually measured it. It had a maximum relative error of 211x.
211 times wrong. It is literally like, it's like trying to find the exact weight of a single feather, but instead of putting it on a small digital scale, you put an entire battleship on an industrial shipping scale.
Right.
Then you put the battleship and the feather on the scale together and you try to subtract the difference. But the shipping scale rounds to the nearest ton, so the feather's weight is just completely lost in the rounding error of the battleship.
That is a perfect way to visualize it. You built the battleship purely as an algorithmic shortcut to weigh the feather, and in doing so, you completely destroyed your ability to actually measure it. But remember, the most insidious part of this entire trap, the polite failure.
Right, because earlier we established that this code didn't actually crash.
Exactly. It doesn't throw a nana number error. The GPU doesn't freeze or lock up. Because mathematically, subtracting 2 huge rounded numbers still produces a finite number. It just produces a deeply incorrect one.
That's terrifying.
So the backtest finishes running in absolute record time, and it returns this totally smooth, plausible-looking equity curve, a curve that is built on pure, unadulterated fiction.
And the charting software just plots it like everything is totally fine. So if the hardware is fundamentally the constraint here, like if Apple Metal simply refuses to give us the 64-bit precision we need to hold that battleship, do we just have to, abandon Apple GPUs entirely for this kind of financial backtesting?
Not at all. And this is where the engineering gets really clever. We know we can't force Float 64 onto Apple Metal. We literally can't change the hardware. So the solution have to be a total reimagining of how we ask the mathematical question in the first place. We have to change the sum itself, not the bits.
Okay, what does that actually look like? If the O of n prefix-sum trick is a trap because it creates these massive running totals, what is the escape route?
The escape route is a direct windowed convolution.
Direct windowed convolution. Okay, let's translate that. What are we actually doing differently in the code?
Well, instead of keeping a massive global running tally that grows out of control across all 150,000 bars, you just abandon the global sum entirely. You literally just slide a small window, say your 200 bars, across the data step by step.
Okay.
In the MLX framework, which is Apple's machine learning array library, this is done using a specific primitive command called mx.conv1d.
But wait, hold on. If we are sliding a window and calculating each 200-bar chunk individually from scratch, aren't we basically going back to the slow way you mentioned earlier? How does this fix the precision problem without completely breaking our speed?
Well, it fixes the precision problem because of how the mathematical weights are applied inside that small sliding window. In this direct convolution method, the weights you multiply the prices by are pre-normalized so that they sum exactly to 1.
Oh, I see. Okay, so if you have 200 fractions that add up perfectly to 1 and you multiply them by a price of 30,000, you aren't just taking tiny slices of 30,000.
You're hitting on the core of the fix right there. Every single partial sum you calculate stays right around the actual price scale. If the price is 30,000, your internal math is hovering right around 30,000. Nothing ever comes remotely close to that 16.7 million ceiling of fp32.
You never build the battleship in the first place. You just weigh the feather directly.
Exactly. There is no catastrophic cancellation because there are no massive numbers to cancel out. And the results of this are just stunning. By making this one architectural change to the code, the maximum relative error plummets from 211x all the way down to 8.2 times 10 to the negative 7th.
Down to 10 to the negative 7th, meaning the error is incredibly microscopic at that point.
Right. It equates to 7 significant figures of exact agreement with a perfect float64 CPU reference model. Mathematically, it is pristine.
Okay, the accuracy fix makes complete sense to me, but I have to push back a little on the performance claim. Because earlier, we established that quants use that dangerous prefix-sum trick because it's O of n, it scales beautifully.
Right.
But calculating every 200-bar window individually, multiplying all those fractions and sliding it across, that is technically O of n times p, meaning it inherently takes more steps depending on the window size. Doesn't doing fundamentally more steps mean it just has to be way slower? Isn't that defeating the entire purpose of porting this to a GPU?
Well, if you were running this on a standard single-thread CPU, meaning a processor that literally calculates one single thing at a time sequentially, then yes, an O of n times p algorithm would be drastically slower. But this highlights the fundamental difference between CPUs and GPUs.
How so?
Think of CPUs like a single, incredibly fast chef cooking one meal at a time. GPUs are like 10,000 average speed chefs cooking 10,000 meals simultaneously.
Ah, the parallelization.
Precisely. The GPU doesn't calculate one window, then slide over and calculate the next. It computes the dense convolutions across the bars of data and the thousands of parameter combinations simultaneously. So even though it is executing more absolute mathematical operations, it handles them so efficiently in parallel that the convolution method is actually 55.9 times faster than highly optimized single-thread CPU code.
Wow. Okay, so by just changing how you frame the math to better suit the hardware's architecture, you get the blinding speed of the GPU and you get the pristine accuracy.
You completely sidestep the trap. But solving the math introduces a new, very necessary question about trust.
Right, because if the bad algorithm produced an equity curve that looked totally plausible, how can you trust that this new quote-unquote good convolution algorithm is actually right? Because as we just saw, eyeballing the chart is a guaranteed way to get fooled.
Visual verification is totally useless here. We need mathematical proof. We need to check what are called discrete invariants.
Discrete invariants, meaning things that are absolute, countable, and shouldn't change no matter how you calculate them, like the actual trades themselves.
That's the ultimate source of truth. You don't compare the squiggly lines of the equity curves. You compare the actual actions this strategy takes. So the author of the article took the output of this new fast fp32 GPU method, and they compared it to a trusted, agonizingly slow float64 CPU reference method. And they simply counted the actual buy and sell orders generated by the strategy.
The moment of truth. Out of curiosity, how many total trades are we talking about in a backtest of this size?
Across all the parameter combinations, there were 479,016 total trades executed. And out of nearly 500,000 actions, only 90 trades shifted when using the new GPU method.
90 out of almost 500,000. That is a 0.019% difference. That's incredibly close. But, well, hold on. If the new convolution math is completely fixed and perfectly avoids the exact integer limit trap we talked about, why did any trade shift at all? Shouldn't the difference be exactly 0?
It's a very natural assumption to make, but it ignores the physical reality of the 32-bit space. Even with the fix, we are still using FT32. It still has a tiny bit of wobble at the very furthest decimal places.
Just normal floating point fuzziness, not the massive 8 million unit errors we saw before with the prefix sum.
Right, exactly. Now, imagine two moving averages crossing over each other to trigger a bias signal. Usually they cross decisively. But occasionally, the difference between the two curves on a specific minute is incredibly tiny, say 0.03. On those razor-thin borderline bars, that microscopic fp32 precision wobble can occasionally move the crossover point forward or backward by just a single bar. It shifts the trade slightly.
I understand it's not a catastrophic failure of the algorithm. It's just the inherent fuzziness of making a borderline decision in a 32-bit environment.
Exactly. It's bounded, explainable variance. And this actually brings us to a really fascinating analytical pitfall that the author points out. They call it the decoy metric.
What's the decoy metric here?
When testing for parity between the two models, if you just look at the 80 different parameter combinations they ran and you ask, hey, how many of these combos showed any difference at all? The answer is 37 out of 80, nearly half.
Wow, yeah, if you present that metric in a boardroom, that nearly half of your parameter sets are acting differently, it sounds like the entire system is completely broken.
It sounds alarming, right?
Yeah.
But it's completely worthless information because every parameter combo has thousands of crossovers. Statistically, almost every combo is going to have at least one borderline crossover that wobbles by a single bar due to normal fp32 variance. So simply asking, quote, did it differ, is a decoy. You have to measure by how much it differed.
That makes total sense. 37 combos technically differed, but they only differed by a grand total of 90 trades out of 500,000. That 0.019% shift is the true signature of a correctly functioning fp32 method, whereas the old method was off by a factor of 211.
Exactly. Knowing what normal variance looks like versus catastrophic failure is just essential. So we have the correct math. We have the blazing fast convolution. We've proven it works by counting the discrete invariants. You'd think we were ready to deploy.
I sense a but coming.
But when we zoom out and look at the performance of the entire end-to-end backtesting system, we hit a classic computer science wall. Let's look at the final speed numbers for a second. The entire system ran at 779 parameter combinations per second. That is 2,796 times faster than a standard Pandas Python baseline and 19.6 times faster than the absolute best serial CPU code.
19.6 times faster overall. But earlier you said the convolution math alone was 55.9 times faster. Why is the whole system only 19.6 times faster? Where did all that extra speed bleed out?
We are seeing a perfect real-world execution of Amdahl's law.
Amdahl's law. Let me see if I have this right. It's the idea that once you make the absolute slowest part of your system infinitely fast, the second slowest part immediately becomes the new bottleneck that ruins your day.
That's the harsh reality of optimization in a nutshell.
Huh.
The GPU annihilates the math convolution so effectively that doing the math is just no longer the slow part. The new bottleneck is what happens after the math is done.
Okay, what is that?
It's the process of extracting the actual trades. Walking through the data, finding where the moving averages cross, and recording the buy and sell orders. That is an O of n sequential process that the author intentionally kept on the CPU using float64 to ensure total accuracy with the reference model.
Okay, so the math is lightning fast. But reading that data and turning it into an actual list of trades is dragging the average down. So why not just put the trade extraction on the GPU too? Why not write a custom piece of software, like a kernel, that runs directly on the graphics card and keeps everything in one fast place?
Because of something called the IPC tags, interprocess communication. Past a certain point of optimization, making a system faster isn't about arithmetic anymore. It's about orchestration. It's about where the data physically lives. Moving data back and forth between the CPU and the GPU takes time. Writing a massive, complex custom metal kernel just to sequentially extract trades might claw back a tiny sliver of performance, but the development cost is huge, and you risk introducing an entirely new set of hard-to-find bugs.
Right, it's the ultimate law of diminishing returns. You cleverly optimize the heavy lifting, you got a massive, nearly 3,000 times overall speed up compared to standard tools, and you just take the win.
You take the win, absolutely.
Yeah.
But you can only take that win because you mathematically prove that the numbers you are winning with are actually true.
Which really distills this entire deep dive down into a few vital takeaways for you. First, you have to know where your hidden intermediate numbers live, not just your inputs and outputs. Second, you have to avoid those big then-cancel anti-patterns, where you build a massive battleship just to weigh a feather. And third, you can never trust a fast system without verifying it, using a discrete invariant like counting the actual trades against a slow, trusted oracle.
Because, as this entire architecture proved, fp32 doesn't fail loudly. It fails politely with numbers.
It fails politely. This whole scenario happened in a highly scrutinized professional algorithmic trading environment, and the error was almost missed entirely because the output looked perfectly normal. Which leaves me with a pretty chilling final thought for everyone listening today.
Let's hear it.
We live in an era where AI, machine learning, and data science are aggressively pushing everything onto fast, fp32 constrained GPUs. Every industry wants to save compute time. Everyone wants to save money. So how many other critical models are out there right now? Models that are making decisions about your financial portfolio, your insurance rates, or your medical diagnostics. How many of them are silently succeeding today, politely churning out plausible, highly optimized garbage?
It's a reality check that every developer and data scientist really should be wrestling with right now.
Truly. Well, thank you so much for joining us on this deep dive. Keep questioning the data you trust. Always look under the hood, and we will see you next time.